Hi, this is Mark. For this video, I'm going to cover set number 4 of this series. I'm covering a Calculus 2 midterm exam. And for this set, I'm going to cover questions 10 through 12. For this question, we're covering solving the indefinite integral of this 1 divided by the square root of 4x squared minus 9 dx. So the key right here is we're going to focus on the radical expression, 4x squared minus 9. And essentially, so we're going to focus on this 4x squared minus 9. Try to simplify it in such a way to eliminate it from the radical expression or the square root. So we know this, we need to focus on a few things. For one, the first identity we need to focus on is if we take the tan squared x plus 1 equals to secant squared x, and then if we subtract 1 from both sides, we're left with tan squared x equals to secant squared x minus 1. So that's critical information. Another thing we know is if you take 2x and you square it, you get 4x squared. So now what if we let 2x equal to 3 secant theta, then 2x squared, which is 4x squared, happens to equal 9 tan squared theta. So therefore, 4x squared minus 9 happens to equal 9 secant squared theta minus 9. And then equals to 9 secant squared theta minus 1, taken out of 9, and then by using star, we get this expression. So 9 tan squared theta. So therefore, the square roots of 4x squared minus 9 happens to be the square root of 9 tan squared theta, which is this 3 tangent theta. But we also need to solve, like if we know that 2x equals to 3 secant theta, then x equals to 3 divided by 2 secant theta. What I did is I just divide both sides by 2, and so therefore dx with respect to theta equals 3 divided by 2 tan theta secant theta. So therefore dx equals to 3 over 2 tan theta secant theta d theta. So now we're evaluating now the integral, the indefinite integral now of 1 divided by the square root of 4x squared minus 9 we know is our dx. So now we're inputting the 1 over the radical, which is this 1. We already solved the radical was 3 tan theta, and then dx becomes, we can take the 3 over 2 outside. We're left with tan theta secant theta d theta. So the key here is we eliminate now the tan theta, so this becomes 3 divided by 2, because tan over tan is just 1. We also have a 3 over here, so we can take out 1/3 times 1/3. Tan over tan theta is 1, and we're left with secant theta d theta. Secant theta. Okay, so now we can separate this to be 3 over 6, which is again 1/2, so that's 1/2 times the integral of secant theta. And now what we're going to do is we're going to use an identity. So we can let 1 equal to secant I believe it's secant squared theta plus secant theta tan theta. Or secant, no. So, no, we're going to let this equal to, yes. Actually, we're going to focus on this. I'm going to eliminate that. Hold on. So actually what we need to do is we need to focus on, we're going to let 1 equal to secant theta plus tan theta divided by secant theta plus tan theta. So we can multiply this secant theta by 1 and it's still the same. So therefore, this equals to 1/2 times secant theta times secant theta plus tan theta divided by secant theta plus tan theta d theta. So now what we have is when we combine it, so basically this becomes secant squared theta plus secant theta tan theta all divided by secant theta plus tan theta. So now we're going to use a substitution. Let u equal to secant theta plus tan theta. Then du happens to be secant theta tan theta plus secant squared theta d theta. So of course we have d theta out here. So now, because I took this derivative of secant and also we have the derivative of tan. So basically what we had before is derivative of tan, which is secant tan, and the derivative of secant is, I believe, derivative of tan is secant squared theta, and then derivative of secant is secant theta tan theta. So we combine these, now we have 1 over u. So essentially now we're going to take this integral equals to 1/2 the integral of 1 over u du. Because the du took care of the numerator, and the u takes care of the denominator. So this equals to 1/2 ln u. So by resubstitution, we know u equals to 1/2 ln secant theta plus tan theta. So that's the key right there. And we notice that we let, was it 2x equal to 3 secant theta? So therefore secant, so if we divide both sides by 3, so we have 2 over 3 x equals to secant theta. And then essentially we have, so then we have to take care of tan theta, but we know that, or what is it? Okay, so we know that tan squared theta equals to secant squared theta minus 1. So tan theta, if we take the square root of both sides, equals the square root of secant theta minus 1, which equals to the square root of 2 over 3 x minus 1. So therefore, the integral equals to 1/2 ln 2 over 3x plus the square root of 2 over 3x minus 1. And there we have it. So the key is we have to put it back into, you could keep it as theta if we're doing in terms of theta, but typically you want to revert back to the original form and make it in terms of x. So we resubstituted back to get this form. So there's that problem. And then, so for the next problem, it says evaluate the following integral. Draw a box around final answer. Okay, or answer. Okay. So with this one, we're evaluating the defined integral from 0 to pi thirds sine 3x cosine 4x dx. So the key here is, so we have sine. So we want to simplify, because if we make like u equal to sine, well, du is going to be cosine x and so forth. We got to somehow eliminate it to where we single out the terms. So for this case, what we can do is we can write this as equal to sine x, sine squared x times cosine 4x, and then you have dx, or so basically we have the integral. And so we know that key identity is sine squared x plus cosine squared x equals to 1. And so therefore, sine squared x, we move this over, equals to 1 minus cosine squared x. So therefore, now the integral becomes 0 to pi thirds. We have sine x, 1 minus cosine squared x times cosine of the 4x dx. So in this case, we let u equal to cosine x. So du is negative sine x dx. So therefore, negative du equals to sine x dx. So I took care of sine x dx right here. That's du. That's negative du is sine x dx. So now we have the integral is 0 to pi thirds. So we're going to take negative, because we have to make it carry the negative sign. And we're left with 1 minus u squared times u to the 4th du. So essentially this is equal to negative 0 to pi thirds. Well, we have u to the 4th minus u to the 6th du. So anytime we're working with u, we let u equal cosine x. So now we're going to take actually, this is integral from u1 to u2. So this is supposed to be when we do u, we have to convert it to u coordinates. So like for instance, if u equal cosine x, so what u1 equals to cosine 0, which is 1, and then we have the upper bound is cosine pi thirds, which happens to be I believe it's 60 degrees, and then the cosine is going to be 1/2. Or we can use these two cases. So I believe, yes. Or we could revert back. So in this case, this is going to be, we have u to the 4 minus u to the 6 du. So basically now when we evaluate it, we're left with u to the 5 over 5 minus u to the 7 over 7, evaluated from 1 to 1/2. Okay, so this happens to be equal to 1/2 to the 5th over 5 minus 1/2 to the 7 over 5. And then we have minus 1/5 minus 1/7. So that ends up being a large, or The 1/5 is okay, I believe that should be right. Okay. And whatever that comes out, or we're just, if we convert it back into, or here's another case, or we could do equal to, because u is cosine, it's just cosine 5x over 5 minus cosine 7x over 7, and then this is evaluated from 0 to pi thirds, and we're just inputting, this is just cosine 5 pi thirds over 5 minus cosine 7 pi thirds over 7. And then, in this case, we're going to subtract cosine 5 0 over 5 minus cosine 5 7 to 0 over 5. And then whatever that value, whatever, the input becomes. So, I believe for this case, yeah, I'm just not going to use it right now. But that's how you solve this problem, and already verified before. And you can always use it interchangeably, but if you convert back into x, you got to use the original because they're a function of x and dx, for instance. But if you use u coordinates or the u substitution, you have to change the range or the endpoints as a function of u, so that way it's consistent. So then the next problem says use the method of partial fractions to evaluate the following integral. Okay, so for this case, we have x squared minus x plus 1 divided by x squared times x squared plus 1. So for this case, we can take this integral, okay, so what we have right here is we have two different, components. So we have ax, to do ax plus b over x squared plus bx plus d over x squared plus 1. Okay, so basically there's two different terms with degree x squared, so we have to drop a degree on the numerator, degree 1. And then right here, what we need to focus on is, okay, so now if we multiplied both sides, so now we multiply both sides by x squared times x squared plus 1. So basically now, if this is the integral, so then the integral equals to, the x squared cancels. If we multiply x plus b times this whole term right here, we notice the x squared over x squared cancels, so it's this ax plus b times x squared plus 1, and then we have plus okay, so plus, so that's the key, we're multiplying. Okay, that works. And then plus, and then the x squared plus 1 cancels out when we multiply, and we're left with bx plus d times x squared. And we know that this whole thing equals to x squared minus x plus 1, which is the numerator. So basically we got rid of the denominator terms, and so we can break this apart, and we're left with ax cubed. So I'm converting, I'm transferring here to here, and then we also have here to here. So we have ax cubed plus ax times 1, and then we also have bx squared, and then we have to transfer here, plus bx squared plus b. So that takes care of all that. And then we also have, we have to transfer bx to x squared plus bx cubed. And then we have plus dx squared. I believe I got that all. Okay, so the key here, we have to combine the cubes together. So we have 2 cubes. And then we combine the squares together. And then this is just x to the 1 power. So we combine the x's. And then so when we take the cubes, we have a plus b x cubed. And then the squares, we have plus, let's see how many squares. We have 2. Oh yeah, we're carrying, okay. Okay, so we have dx squared and bx squared, so plus b plus d x squared. And then for the x, we have plus ax. Is that it? I believe. Okay. Okay, ax. So we just have ax, and then we have plus b. Okay. Equals to x squared minus x plus 1. But we notice right here is we know the cube is 0. There is no x cubed term. So we know a plus b must equal to 0. Okay, now we know also there's just, this is a coefficient of 1 by the x squared. So b plus d, so here's the key terms. We know b plus d must equal to 1. Because that's, and then we have the x term is -1. Okay, so that means a equals to -1. And then relaying it back here. So what we have now is -1 plus b equals 0. So that means b equals +1. Okay, but the last term is we have plus b, which is a 1. Well, that's satisfied. That's satisfied there too. A is -1. Is true for that case. Has to hold. Since b is already 1, okay, there we verified it right here in both cases. Okay, if b is 1 and b plus d is 1, so we know b equals 1 and we know b plus d equals a 1, that means d equals 0. So we have all our terms. So therefore the integral remember we have okay, x plus b over x squared. So integral equals to ax plus b over x squared. So we have a equals a -1, -x, plus b is 1 over x squared, plus we have bx plus d over x squared plus 1. So bx plus d is 0 over x squared plus 1. And then we all of this by dx. So key is we break it into parts. So we have the integral of -x. Right here, we can break this whole thing into pieces. So basically, this is -x divided by x squared plus dx plus the integral of course, we're evaluating, I believe. Okay, it's indefinite. So then we have to add plus c at the end. So we have negative x over x squared dx plus, okay, this is 1 over x squared dx. And then we have plus the integral of x over x squared plus 1 dx. We split it all together. So right here, this breaks into negative 1 over x dx plus the integral of 1 over x squared dx plus the integral of x over x squared. So we're going to work with this, let be this v1, this v2. So we're going to focus on 1. So 1 equals, we know, equals to ln, negative ln x. We're going to add plus c at the end. So this is negative ln x. 2, well, this is just the integral of negative, or x to the negative 2 dx. So this is equal to, remember you add 1, so it's x to the negative 1 over negative 1. So equals negative 1 over x. And then for 3, okay, for that one, let u equal so du equals 2x dx. So 1/2 du equals x dx. So we took care of the numerator by 1/2 du, and we have the denominator. So basically this is, it's going to be, we got 1/2, 1 over u, because 1 over u is this x squared plus 1. We took care of, du takes care of the rest. And this is just 1/2 ln u, or putting it back together, 1/2 ln x squared plus 1. So therefore, we're going to take 1 plus 2 plus 3, which is integral, which equals to negative ln x minus 1 over x plus 1/2 ln x squared plus 1 plus c. So there you have it. So that's how you solve this integral. And of course, it's key to break it into components so you don't make less algebraic errors. And I'm just going to end at this point, and I'll see you next time.